Barely Berry Jr. here, back as promised to continue going through uh, some physics, graduate level physics. So what I'll do is continue the reading from earlier, where I was trying to get to the Virial theorem. It's promised I'm back by 8 o'clock. And we'll go ahead and get started. I'll continue from my previous. So, and this is a new section, so it shouldn't be too difficult to just drawing where you're at right now. Just the same topic, just say the next section afterwards. So let's go ahead and go. I'll scrolling through to see how many pages I have to the Virial theorem. And here's my let me make sure my stream is behaving properly. Seems to be. Okay. All right. So we're going to continue from where we left off. Previously, we ended up getting the equation for energy, the conservation of energy, in terms of the kinetic energy in the radial derivation, and the potential energy, which is the interaction between the two bodies that are orbiting. So we'll continue from here. And those who's watching, thanks for watching. I'll be sure to drop a line. I am checking the chat here. So if you have any questions or comments, be sure to drop a line there. I am looking at that. And just to say hi. And so we have 3.3. I'm going to try to get through the Virial theorem. Equivalent 1D and orbits. Although we have solved the one-dimensional problem formally. Okay. I mean, it still seems like a bunch of random equations to me at this point, but we do have a homework assignment, so perhaps it'll make more sense when I do the homework, which I may do live with you all as well. Although we have solved the one-dimensional problem formally, practically speaking, the integrals 318 and 320. So these two are usually quite unmanageable, which I found out earlier. I still don't know what they did to get this form of the integral in terms of R. And in a specific case, it is often more convenient to perform the integration in some other fashion. Before obtaining the solutions for any specific force laws, let us see what can be learned about the motion in the general case, using only the equation of motion and the conservation theorems without requiring explicit solutions, okay? For example, with the system of known energy and angular momentum, the magnitude and direction of the velocity of the particle can be immediately determined in terms of the distance r. The magnitude v follows at once from the conservation energy in the form, which we discussed earlier. I mean, this is pretty much this equation here, 313. If that equation were in in Cartesian coordinates. So we have E equals 1/2 mv squared plus vr, or we're going to solve for v. 1/2 mv squared equals vr minus e. V squared equals 2 over m vr minus e. And we can square root that. 2 over m. Oh, did I swap it? I think I swapped it. Yeah. E minus. When I swap sides, I forgot to swap the order as well. So this is 3.21. The radial velocity, the component of r dot along the radial vector, has been given in equation 316. Okay. So this is basically, as I understand it, the particle going outward and nearer to the uh, center of gravity. Radial velocity combined with the magnitude v, this is sufficient information to furnish the direction of the velocity. Okay. So we have it going outward and inward. Alternatively, and this is the asterisk, alternatively, the conservation of angular momentum furnishes theta dot, angular velocity. And this together with r dot gives both the magnitude and direction of r dot. So r dot and v get the direction, and theta dot plus r dot is direction and magnitude. The equation of motion in r with theta dot expressed in terms of L, equation 312. So 312 is the equation of motion of r expressed in terms of L squared. If I just put this to the other side, and again, we got that by what? Taking theta squared and substituting it into 3.8. That's only r and its derivatives. It is the same equation as would be obtained for a fictitious one-dimensional problem in which the particle of mass m is subjected to a force. Okay. The significance of the additional term is clear if it is written as mr dot squared equals mv theta squared over r. Okay. So perhaps they're utilizing the idea, ironically, that we were talking about in foundations, which I believe v equals theta dot r. So v squared equals theta dot r squared, or theta dot squared r squared. So theta dot squared equals v squared over r squared. And f prime equals f plus L squared over mr cubed. So see how this relates. I believe I'm plugging this into, what am I plugging this into? 3.08, I believe. Sure. You're writing. I'll copy this down. Right, so this means this equals mu r squared. Well, it's not squared. I'm not sure where they're getting this mr theta dot squared from. See mr squared theta dot, but not mr theta dot squared. Okay, so I guess they're just literally just writing the additional term. I'll take it as that. So say this is mr theta dot squared, which equals m v squared theta over r. M squared equals m r v squared over squared, which equals m v squared r. So it seems that's what they did. And v equals theta r, because if you have a angle theta that's changing in that direction, and r is going to place the point here, and those two together is going to give you the velocity, the angular velocity that is changing by. And that's what I think omega is theta dot. So hey, classical coming in handy here as well. Foundations. An equivalent statement can be obtained from the conservation theorem of energy by equation 3.15. Right? The motion of the particle in R is that of a one-dimensional problem with a fictitious potential energy. So this is fictitious. Prime equals 1/2 L squared over mr squared. So this is 3.22 prime. And this is 3.22. And let me check the stream. Make sure it's going properly. Stream widget type deal is saying that it went off. Then so let's take a look and see. So it seems to be okay. Seem to sound okay. So I might let this check this out just for a little longer. Okay, everything seems good. So if somebody pops in, please let me know if um, difficulty with the stream. As a check, note that F equals negative partial V over partial R, which equals FR L squared over MR cubed. All right. Even though I don't see why there's not a negative on the L squared over MR cubed, because it's R to the negative 2, then negative 2 would take its share of the half, negative 3. All right, keep going. Which agrees with equation 3.22. The energy conservation theorem 315 can thus also be written as E equals V prime plus 1/2 M R dot 3.15 prime. Welcome who's joined. As an illustration of this method of examining the motion, consider a plot of V prime against R for the specific case of an attractive inverse square law force. F equals negative Q over R squared. The positive K, the minus sign ensures that the force is toward the center of force. The potential energy for this force is negative K over R. The corresponding fictitious potential is V prime is negative K over R plus L squared over 2mR squared. Such a plot is shown in figure 3.3. The two dashed lines represent the separate components, negative K R and L squared, 2mR squared. And the solid line is the sum, V prime. Okay, interesting. Professor drew this on the board. So you have the potential on the y-axis, energy on the x-axis, as far as I can tell. V versus R. You have potential on the y, radius on the x, and it's just energy levels that the energy of the system is noted by the horizontal lines. Okay, let's draw this. This is V prime. And utilities dotted. And this is the sum, like so. This is V prime. And, oh, okay. R is actually here. So R, this is L squared over 2mR squared. And this is V equals negative K over R. The negative, so if K is positive, its force is inward. And I remember Professor was telling us how this signifies a circular orbit. Since the slope of V is 0, it doesn't change. If I'm remembering that correctly, I'm sure we'll get to it in the book. the equivalent one-dimensional potential for a active inverse square law force. Let us consider now the motion of a particle having the energy E1. So I'll draw E1 on here. Like so. As shown in figure 3.3 and 3.4. Clearly, this particle can never come closer than R1. All right, so we have R1. Particle can never come closer than R1. That's where the energy crosses the radius. Potential is equal to that energy. It crosses at that radius. So I guess it either has too much or I guess it has too much energy. That makes sense. It was orbiting very fast. It could only get so close and still keep a stable orbit. So if it's orbiting very fast, the speed will stop it from getting so close. Considering that the total energy, E, is the potential energy plus the kinetic energy, and that has to be stable, so the energy is going to be very high. So it seems to make sense. Clearly, this particle will never come closer than R1. Otherwise, with R less than R1, V prime exceeds E1. And by equation 315 prime, the kinetic energy would have to be negative, corresponding to an imaginary velocity. All right, that's 315 prime there. On the other hand, there is no upper limit to the possible values of R, so the orbit is not bound. Particle will come in from infinity, strike the repulsive centrifugal barrier, and be repelled and travel back out to infinity. In figure 3.5. An orbit for E1 corresponding to an unbounded motion. All right. So this would be like that object Oumuamua that at least one physicist thought is some evidence of extraterrestrial technology or something. You noticed by its speed and trajectory, it came from outside the solar system, so it was really an interstellar object. And it just passed through the solar system and kept going. So it is quite amazing that we had a sort of visitor from outside the solar system. So I wonder where it's at now. Pretty sure the sun altered its trajectory, so interesting to think about. The distance between E and V is 1/2 mr squared, i.e. proportional to the square of the radial velocity, and becomes 0 naturally at the turning point. I'm thinking about that. At the turning point, I guess at that point is 0 potential and total kinetic energy at the same. The turning point R1. Yeah, so R1 is as close as it's going to get. It has the lowest potential energy, 100% kinetic energy, right? At the same time, the distance between E and V on the plot is the kinetic energy, 1/2 mv squared, at a given value of R. Thus, the distance between V and V prime curves is 1/2 mr squared, theta dot squared. These curves therefore supply the magnitude of the particle velocity and its components for any distance r at the given energy and angular momentum. This information is sufficient to produce an approximate picture of the form of the orbit. I'm not seeing how they're getting this. The 1/2 from r dot, I think that's the radial distance. The v dot, he said earlier, is the magnitude of the movement, if I remember right. Okay, now that's in terms of energy and potential. And r squared theta dot squared, that seems to be in spherical. I believe that's the one that gives us the direction and the magnitude. Or close, there's no dot there. For energy E2 equals 0, a roughly similar picture of the orbital behavior is obtained. So for energy E equals 0, right there at R. For any lower energy such as E3, we have a different story. So E3 about here. E3, E3, E3. Got that. And so in addition to a lower bound R1, there is also a maximum value R2. Okay. So this will be R1 for that curve. This would be R2. And this is only the only R1. This is the only R1 for that energy. This one has R1 and R2. So these only have R1, so they're not bound. They just pass through and keep going. Welcome who joined. Let me know if you have any questions and comments. We'll look at orbits, the orbits of bodies orbiting through a central force. And then I'll get to the Virial theorem in a bit. Let me know if you have any questions or comments, or just drop a line and say hi. Thank you for joining. And remember to like and subscribe if you haven't already. So we have R1, R2 bounded, and R2 cannot be exceeded by R. Hey Lisa, how you doing? Oh, let me go ahead and yes, I am doing well. Let me correct that. Boom. Awesome. Hey Jeremiah. So yes, doing well in graduate school now. So the physics is harder, more challenging. So what? Getting it done. When I'm taking classical mechanics, foundations, where I'm reviewing all of undergraduate physics, or remember the majors of it, and doing a research course where I'm doing models of stars, and also quantum mechanics, graduate quantum mechanics, which is a whole lot of Dirac notation. So it's going okay, having fun. This interests me because I know it relates to the orbits of stars as well. So many stars are binary stars, where there's two orbiting each other. So I'm sure this will come in handy in a bit. Thank you. In addition to a lower bound, there's also a maximum value R that cannot be exceeded by R with positive kinetic energy. The motion is then bounded, and there are two turning points, R1 and R2, also known as axial distances. So, I mean, it seems to correspond to the nearest and farthest points in the orbit. This does not necessarily mean that the orbits are closed. Oh, okay. Scratch that idea I was thinking. All that can be said is that they are bounded, contained between two circles of radius R1 and R2, with turning points always lying in the circles. Man, they should have did a better job of placing these images. All right, let's take a look and see the nature of the orbits for bounded motion. All right, it is quite ugly. So, yeah, obviously these are not drawings for, like, like we would draw like the sun and something going around the sun. I guess these are just literally just drawings representing the potential of something like the force, uh, like free body diagrams where you have the normal force, for instance, and the gravitational force. So, I mean, what this reminded me of what my professor did in class, even though she didn't draw this one, but she did draw the one I'm drawing right now. And we'll see how soon I can get to the Virial theorem. I'm determined to get to the Virial theorem so I can be ahead on the class. Let's see if we can get there. At least a few pages are skipped with these big giant diagrams, right? So we looked at this one, unbounded, can't go closer than R due to its energy. Also, kinetic energy will be negative. So that's like a Muir that just came into the solar system and went back out. That's what it reminds me of. So, and this does seems like the Muir path. You can imagine that we dot right there. The point about which it goes is the central force, which in our case would be the sun. So Muir just came in, went around, was attracted to the sun, and the sun shot back out. And I suppose when it was coming to the sun, it was speeding up here. When it was going this way, it was slowing down a bit, but like Newton's first, what law is it? Newton's third law, equal and opposite? No. Yeah, it must be equal and opposite. Newton's third. It both pulled on each other the same, so they sped up. Both pulled each other the same on the other side, so they slowed down, but they should have pushed and pulled equal amounts. So Muir should be going at the same speed it entered the solar system at, and I guess there might have been some altering due to the heat of the sun. Maybe that did something. Welcome the new person that joined. We're doing some orbital mechanics and graduate level physics. Be sure to drop a line, say hi. Let me know if you have any questions or comments. Like, subscribe if you haven't. Well, trying to just, I guess there's not anything else. You want for unbounded. Almost to the Virial theorem. This is one we were looking at with E3. Just didn't write E3 on it. So it is bound, but not necessarily closed. So I guess it could still escape potentially. Seems odd. Bound, but not closed. It does not mean the orbits are closed. Right? And now we're at E4. So these images are placed such that I have to scroll a lot. At least I'm going to draw them when they're discussed. So we have E4 here. This will be the circular orbit, so I remember from class. Let's confirm and see. E4. We have, if the energy is E4 at the minimum of the fictitious potential, as shown in figure 3.8, and the two bounds coincide. All right. So in other words, instead of having R1 and R2, R1 and R2 is there. So I'll just call this R12. In such case, the motion is possible at only one radius. At only one radius. Or, oh, I see. R dot equals 0. That would make it circular. So there's only one radius. The radius doesn't change. The potential energy is constant. So if the star is orbiting, or let's say if the planet is orbiting the sun and going like this, it has a smaller potential energy here and a larger potential energy here. So we have R changing, that's R dot. We have V changing with respect to R. But if it is a circular orbit perfectly, then there's only one orbit. So R dot equals 0. And since R dot equals 0, there's only one potential. So the change of potential is 0. And thus, since it's not changing, the slope is flat. We know from the crit, those who took math. Lisa says this is well past my level of physics, so just trying to follow. I'll try to explain in a bit more detail. Thanks for saying, Lisa. So the idea is basically, as I understand it, so I'm learning this at the same time. This line here, maybe I should highlight it, is illustrating the potential of an object in orbit around another object as far as how the potential goes. So to relate it to something that we may be more familiar with, like say we have a rock on a cliff and it has a potential energy that if I drop it off, it has a potential energy, mgh, the mass times the gravity, the force of gravity times the height. And as it falls, it loses potential energy, but it gains kinetic energy. So down here, the kinetic energy will be 1/2 mv squared. So we know that as the distance to the gravitational source of the force is smaller, its potential energy is smaller. And, the thing just drops and hits the earth. And it has 100% kinetic energy, 0 potential energy, and then it stops. What we're talking about here is bodies orbiting each other. So if I have, let's say, a big giant object and a small object, this object may orbit like this, where it has a small potential energy here and a big potential energy there. So that means that there is a change of potential energy. So V is potential energy, and the dr is the change with respect to r, the radius. So this would be r prime. They are different, so it's changing. And this might be, for instance, represented here, where there is a outer bound and a lower bound. So in this case, this would be R1 since it's closer to the object, the force, and this would be, let's say, R2 since it's farther away. And what R12 is saying is, if this thing had a circular orbit, there would be no slope to the potential line because it's even everywhere. So it's flat. The slope of that line is flat. So even though it's curving on either side of that line, at that particular point it's flat, unless we have a circular orbit right there where the potential is 0 because it's not changing, and R is constant because it's staying the same because it's a perfect circle. So now we're looking at the scenario where we're at what? E4. Where'd it go? Right here. Where we're looking at such a rotation was a perfect circle. So the change in R is 0, which just means that R constant. So the change in R is 0. That's why they have that R dot there, looking right here. And the orbit is circular. Remembering that the effective force is the negative of the slope. So this is talking about, which I still need to do the derivative for, force equals negative the derivative of V. It's the negative of the slope V. The requirement for circular orbits is simply that F be 0, which makes sense because this is a perfect circle. There's no net force pushing it out or pulling it in. That's quite interesting. Or, so earlier we had And I'm still not comfortable with that equation, that F equation. But we had this F equals FR L cubed, L squared over MR cubed. So if I take the negative derivative, no, that is a negative derivative. So 3.22 prime is the potential. I take the negative derivative and get FR equals L squared over MR cubed. And is that the same thing that they had? Yeah, L squared over MR cubed. And it's saying it equals MR theta dot squared. I'm not really getting that part either. There's this equation that they had here with the theta dot. I'm not sure how they did that transformation. Where'd that equation go? It was the one that I stopped trying to derive. Yeah, this one here. Seems like they're relating it to this one down here, number 319. All right, let's keep going. We have here the familiar elementary condition for a circular orbit that the applied force be equal and opposite to the reverse effective force of centripetal acceleration. So the centripetal acceleration is the same as the force pulling in. The properties of circular orbits and the conditions for them will be studied in greater detail in section 3.6. Thankfully, that's not the next section. To build on before we get there. Note that all of this discussion of orbits for various energies has been at one value of the angular momentum. Changing L, the angular momentum, changes the quantitative details of the V curve, which makes sense because the equation is over L squared. But it does not affect the general classification of the types of orbits. Well, we change L, the shape in general of the orbit will be the same, like a circular will still be at that point in the potential. For the attractive inverse square law force discussed above, we shall see that the orbit for E is a hyperbola for E1. So they're saying this is a hyperbola. They're saying that E2 is a parabola. Here. And E3 is an ellipse. So, okay. So that's like our orbit, like our orbit around the sun, which makes sense, of course. We go back and forward away from the sun. I forgot that was called an ellipse. I don't remember what name I was thinking about for it. Yeah, I guess I was just thinking elliptical orbit, but it's an ellipse. With other forces, the orbits may not have such simple forms. However, the same general qualitative division into open, bounded, and circular orbits will be true. Open, bounded, circular. For any attractive potential that one falls off slower than 1 over r squared, as r goes to infinity, and 2 becomes infinite slower than 1 over r squared as r goes to 0. Okay? Think about that. So maybe I need to write this. So we have 1 over r squared as r goes to 0, and 1 over r squared as r goes to infinity. So if we're looking at this diagram here, r goes to infinity out there, and r is 0 right here. We was to visualize this with the potential wells, and this shape here is our potential well, like the well of potential of the gravitational pull between the objects, you can say. So as the radius gets really, really big, as the thing gets really, really far away from the center of force, the potential must go away faster than that. That is a good question, Lisa. I guess it must be highly elliptical. At least if the total energy is E3. If the total energy is E3, then the potential will have to fall off slower than that. So it can't be, in other words, it can't be down here. So if it's really, really big, it'll have to be a highly elliptical orbit like our comets. Our comets are like that. But the energy can never go to a point where the energy is down below this curve. Because if it falls off slower, then 1 over r squared, it would be down here on the infinite side. And if it falls off faster, then if it goes to 0, it'll be down here on this side. Is what I'm getting. So it'll either be highly elliptical or even highly, well, I guess it can't be highly circular. It's going to be perfectly circular. But even if it's perfectly circular, I guess there's a limit to how big the circle can be, perhaps. Perhaps there's no limit to how big the ellipse can be. Exactly. I was thinking about the comets. It says Halley comets, for example, is quite elliptical. Yeah, it's a good example. So R2 is really, really huge. R1 is, given the size of its orbit, is almost 0, basically. But yet and still, the potential must fall off fast enough that the energy will never get below this line, or else it will lose its orbit. All right. You could have just said that. I'm understanding that correctly, but it's a textbook, so they have to. Sometimes I think they purposely write in obtuse ways. Maybe obtuse is not the right word. My thermodynamic class, I thought that textbook he wrote pretty straightforward. He wrote in a pretty everyday language. I like that book. The first condition ensures that the potential predominates over the centrifugal term for large R. Okay, which is like you were saying, the far out will be highly elliptical, but it will be pulled back in. Energy will still be contained within that well. Or the second condition is such that for small r, it is centrifugal term. The centrifugal term, it is the centrifugal term that is important. Okay. Not sure about that one. Why use 5 words when you can use 5 paragraphs? Yep, exactly. But I don't think they get paid by the page. Thinking about it, pretty sure it's just like, I don't know. Maybe I need to write a textbook one day. I like to write. The quantitative nature of the motion will be altered if the potential does not satisfy these requirements, but we may still use the method of the equivalent potential to examine features of the orbits. As an example, let us consider the attractive potential. Okay, we're going into an example here. Let's see what we have. So I write my examples. We have VR, the potential is negative A over R cubed, and the force, and let's write this out. We have the force is the negative derivative of V. So this will be negative dV over dr. So that's negative dr of negative A and R to the negative 3. So that's going to be negative, all these negatives. So to be positive AR to the 4th. Looking at that right? So the force is negative 3AR to the 4th. Let's see. Yep. Well, to the negative 4th. Left off my negative. So that's why they have negative 3A over R to the 4th. Lisa says technical writing is not easy. I have to do it for my job, but the bar is not for students to consume, thank God. I think the bar for them sometimes is not for students to consume. Really. The fact is, I'm a little bit serious, right? But for the most part, I jest. The textbooks are all right, but a little bit I am serious. But the fact is, I am getting better at reading textbooks. Like when I first went back to undergrad, it was bad. It was like, dude, this is like in a foreign language. I'm getting a whole lot better, but it just comes with practice. I mean, but this is, I would say, is one of the more, what's the word? Not eccentric, but there's an E word. Not ephemeral, but not eclectic, but there's one of those words that means it's a little bit weird writing, but I guess maybe the best word is more technical, like you were saying. But so we'll make it work. That's the F. The energy diagram is then as shown in figure 3.9. Oh, come on. There we go. I think I could use the same one. L squared over 2r squared. Oh crap. No, I can't. Well, actually, I would have to like draw it differently. Hold up. So they're saying, so everything is the same. But I have that potential. And this reminds me of something Professor wrote on the board as well. Maybe I should make this line bold so it can stand out better. So this is the first potential. Now I'm going to draw the second potential in blue. So we have, oh, this is R1. This is R2. Nope, have to go higher. This is R1. I think I have to make a separate R2 to make this work. So this is a different E. Okay, I have to write a different E to make this work. So it looks like this E is really looks like E1, really. Is either E1 or close to E1. Oh, something like this. So this would be R1 and R2. For this potential. For an energy E, there are two possible types of motion depending on the initial value of R. If R naught is less than R1, the motion will be bounded. R will always remain less than R1, and the particle will pass through the center of force, so it'll just crash into the sun, right? Which makes sense. Is over here. There's nothing to force it out. Not enough energy because energy is up there. At least the maximum energy is up there. In the other direction, it's smaller than R1. For the smallest one, see, I guess it's not going to get over that hump. Let me look at this image again. So R is smaller than R1. Okay. So I guess by the same token, it cannot exist. Since this is turned upside down, before we were saying it can't exist out there. Since this is upside down, it can't exist out here and be bound. So if the energy brings it lower than R1 than is out here, then it just crashes into the sun. It doesn't have enough juice to stay in orbit. And I imagine if it's out here, if it's bigger than R2, then by the same token, it'll fly away. Except it'll fly out the solar system. That's how I'm understanding it. If R is initially greater than R2, then it will always remain so. All right. The motion is unbounded and the particle can never get inside the potential hole. The initial condition R1 is less than R0 is less than R2 is again not physically possible. In class, when the professor was talking about this, I asked her about dark matter because I learned in my relativity class and a few talks as well, like these colloquiums, that apparently dark matter, as far as we can tell, can pass through itself because, I mean, we can't, there's no way to determine it other than looking at its gravitational effects, at least at this point. So the idea is that if you had a particle of dark matter and another particle of dark matter, they will literally go through each other. and then go to the other side of each other. So then they'll be like this, and they could literally have an orbit like this, but they just go through each other back and forth. As far as we can tell, they don't interact with anything except gravitationally. So they'll be able to just pass through each other, and have this weird orbit where they just pass through each other and exchange sides. So it seems to me that a potential like this would be representative of dark matter, but Professor said she wasn't sure about that, or something to that effect, like no orbit in real life would have an orbit like this. I think she said, like the orbits that we're looking at now, which is probably why they keep saying stuff like fictitious. I think they said that a few times. I don't think in real life anything we found has an orbit like this. The everlasting Clinky. Seems cool. I figure we'll find out where dark matter is at some point. Another interesting example of this method occurs for a linear restoring force. Isotropic harmonic oscillator, okay? So we have F equals negative KR, and I won't do the derivative on this one. V equals 1/2 KR squared. There's zero angular momentum, the corresponding motion along a straight line, V prime is V. And the situation is shown as in figure 310. For any positive energy, the motion is bounded, and as we know, simple harmonic. If L equals 0, we have a state of affairs shown in 311. Okay, now they're doing too much. The motion then is always bounded for all physically possible energies and does not pass through the center of force. Okay. I remember my professor was saying this is like a pendulum. In this particular case, it is easily seen that the orbit is elliptic. For if F equals negative KR, the X and Y components of the force are thus. All right. Because F vector will be negative KR vector, which equals negative KX I plus Y J, which is negative KX I plus negative KY J. So they call this Fx, and they call this Fy. Total motion is thus the resultant of two simple harmonic oscillations at right angles and of the same frequency, which in general leads to an elliptic orbit. A lot of ellipses. Yes, I got to the Virial theorem. A well-known example is the spherical pendulum for small amplitudes. Okay, the familiar residual figures are obtained as the composition of two sinusoidal oscillations at right angles where the ratio of the frequencies is a rational number. For two oscillations at the same frequency, the figure is a straight line. When the oscillations are in phase, a circle when they are 90 degrees out of phase, and an elliptic shape otherwise. The central force motion under a linear restoring force therefore provides the simplest of the Lissajous figures. All right. Can't say I understood maybe any of that, but we'll keep on going. A lot of this stuff will make more sense when you do problems. So I'll probably come back during the week. I still have to do that homework. We have an exam on Friday in classical. So I did a video yesterday. Well, I did the first two of the first homework problem, Lisa. I'll probably come back this week to do the rest, because you probably remember when around exam time I like to do all the homework problems and stuff. And the first two were derivatives, were not derivatives, but deriving things. And the next ones would be problems. And the homework two problems were quite interesting. So I'm going to make sure to get you all those problems before Friday, because the exam is Friday. So you can look forward to that. I won't be able to get to that tonight. But I will go ahead and go through the Virial theorem. Let's see how many pages I have here. Oh, not that many. Right here. So we have 1, 2, 3. Only 3 pages. Not that bad. So I'm gonna stand up and stretch my legs. Oof, man. All right. Dig into this Virial theorem. Dig into this Virial theorem, and we'll call it a day. So I have 3 pages to go, then we shall call it 3.4 Virial theorem. And now I should be caught up on class stuff, even though I think she's going to go a bit past the Virial theorem in class, but I'll still call it a day. But she said that this Virial theorem appearing here, she thinks is quite odd, but it comes up in the book, and I like the fact that she goes by the book, like we're going through the book. This says since it's here, we'll cover it. Another property of central force, motion, can be derived as a special case of a general theorem valid for a large variety of systems, the Virial theorem. It differs in character from the theorems previously discussed in being statistical in nature, i.e., it is concerned with the time averages of various mechanical quantities. Consider a general system of mass points with position vectors R and apply forces F, including any forces of constraint. The forces of constraint mean that something that limits the force, like if I'm standing on the planet Earth, a force of constraint can be the fact that I can't go through the Earth. I can't just fall through the Earth. So a constraint is that I can go around the Earth. And of course, we can dig a hole, but I'm just saying, our regular just motion, like driving in a car, unless we fall into a hole, we're not going to just sink through the surface of the Earth. So we can sort of, we're planning a path for our car drive, we can consider that constraint and not count falling through the ground. We just, find ourselves going above the ground. So that's called a constraint, something that limits a force that limits our movement in some direction. So this is saying, so we have a point mass system. And I'll make these smaller. Position vectors are I. So each of these has a position in the coordinate system. And I'll also call this the origin of our coordinate system. Right. And this will be R vector 1. This would be R2, and every one of these will have their own R, so that's why I said they have RI vectors, position vectors, and applied force is FI. Okay, so I guess there's a force being applied to every one of these. We'll call this FI. The fundamental equations of motion are then, okay, so we're going to write to Newton's laws. We have F equals MA equals MV dot, which equals the derivative of momentum. And each one has one of these. So each mass is an I, has an acceleration I, and we have that. This is equation 1.3. We're interested in the quantity, okay? So they call in G the sum of the momentum of everything. So this, I believe, should be more clear because this is technically a review of undergraduate stuff, and it seems pretty straightforward. So I'm getting this, so hopefully you're getting this too. So it's going back to old stuff, which I appreciate. So they're building on that. So they call in G equals the sum of all the momentums at that location we have T I dot R vector R I. So we're interested in the quantity G. And I just realized that's not the derivative of momentum, that's the regular momentum. So they're saying G, whatever G is the sum of all the momentum of all the particles dot producted with the position. So that means that, so basically what's going on is if we have a position vector going in this direction and the momentum is going in this direction, like so, the dot product, let's say it's like this, the dot product will project one onto the other, and it will give us a value of this point where they're going in the same line. And it doesn't matter which one you project onto which, like it'll give you the same answer, even if you projected this one here. So I'm not drawing it perfectly so it won't look the same, but if you did the math on it, you'll see it comes out to be the same. But whatever this G is, it's projected into the same plane, these two vectors. But the summation is over all particles of the system, the total time derivative of this quantity. So now we have the total time derivative. So as a regular letter, not like a partial. Sometimes it could be a partial, where you only derive the terms that actually have P in it explicitly, I guess you could say. But this one is deriving everything that's time dependent. So dg dt equals still the sum I. All right, so let's look at this. Okay. So they're doing a chain rule. So you have to do dt over dt dot r, both of them have an I, plus sum I p I dot dr over dt I. So that's what that is. They use the chain rule, where you take a derivative of each one separately. And so that's writing out what they have there. So I'm going to write it now how they have it. They just have p dot I dot r I plus sum p I dot r dot I. So that's what they have there. The first line is what they did in the background. Oh, and that's what they call that 3.23. Okay, here we go. We're getting into it. So we have our little G thing. I'll write it now how they wrote it there. And again, this is the sum of all of the momentum of all the different particles in this system projected onto the vector of its position. So the momentum projected onto the vector of its position, added up for all the particles, take the derivative of that sum, n dot product. So now we're going to take the first term, and I believe I wrote the first term the same. No, I wrote my first term as their second term. So let me go ahead and swap these so it matches what they're saying. All right, so now the first term matches my first term. And so a dot product can be done in either direction. It gives you the same answer. So let's put it in the same form they have so you can follow along better. So we're going to have the first term here, 1 So we have sum I R dot dot T I equal the sum I of, so I'm going to, what are they going to do? Yeah, made me switch that around just to swap it back. Is that what they did? So I'm going to write a few more steps. So first I'm going to swap these back how I had it before. Dot R dot I. So this is going to equal sum I. Momentum is mass times velocity. Then dot R dot I. And velocity is position derivative I dot R dot I. So they're doing the squared thing. So whenever you have the same thing dot producted by itself, it becomes the magnitude. And maybe I should write this out. So we have R dot I dot R dot I. So this is going to equal R1 dot R2 dot producted with R1 dot R2 dot. So this is a vector written out. So this is going to be R1 dot squared plus R2 dot squared, doing the dot product. So just multiplying the first thing together, then adding it with multiplying the second thing together. So it's the R1s together since they're both first, and the R2s together since they're both second. And if we look at this, x squared equals, or I should say r squared equals x squared plus y squared. So v squared equals vx squared plus vy squared. So this just becomes v squared since they're being added together like that. So this is the background of what they're doing there. So that's why we can go ahead and say equals sum I m I, and this just becomes vi squared. Okay, hold up. You're saying this equals 2t. Oh, okay. So kinetic energy, which we call T, equals 1/2 mv squared. So 2t equals 2 times 1/2 mv squared, which equals mv squared. So that means that since I have mv squared here, I can substitute that in. So I can say now I have equals sum I of 2t. And that's what they did there. Any questions, let me know. And these are still eyed up. All right. So that's the first term. And that was, I shall just copy it down like so. So that still equals 1, our first term. All right. So now we'll take the second term. See what we do with that one. Now we have about 1 page left, and I'll call it a night. All right. Okay, okay. So they're using this. Easy enough. So this equals some I of f I dot r I. Okay. And this equals again this, number 2. So that means if I take my DG equation 3.23, I copy this original thing down, right? So this means this also equals some I of 2t plus some I of force I dot r. All right. This is 3.24. Right? Any questions at this point? Let me know. Let me see here. Almost there. There's a little bit more than one page. All right, let's see what we have. The time average of equation 3.24 over a time interval t was obtained by integrating both sides with respect to t from 0 to tau. Okay. Back up here. So seems like what they're doing here, they're going back to this first equation and taking an integral. After we did all that, time averages. Okay, so we're adding up all the time and then dividing by time. So integrating over t from 0 to tau. I'm not sure exactly what that does. I mean, I guess it, like we know we get an average of, I don't know, numbers 1, 2, 3. The average is 1 plus 2 plus 3 over 3, which is the, number of numbers that we have. So the average is 2. So we can see that that works. So this is the integral form of doing that, which I think is ugly because you're integrating from 0 to tau. I guess integrating from 0 to tau is basically adding from 1 to 3. But I guess it seems sort of deceptive here, but let's say we was getting the average of 1, 2, and 4. You will still divide by 3 because you have 3 numbers. But here, that's what's throwing me off. We're integrating from 0 to tau. We're dividing by tau. I guess it's the integral that's doing something. All right, we'll just keep on rocking. So we have 1 over tau, integral from 0 to tau, dg over dt. So this is dg over dt, dt. So this saying this equals the time average of that. dg time average over dt, which equals the time average of what it is, 2t, the average of 2t, plus some I f I dot r, average of this. All right, so we're doing the average of both. And okay, so we're taking the integral from 0 to tau, and we're dividing by 0 to tau of dt. So the integral basically goes away. So that's what this first part is. Like we're taking the integral of a derivative. Integral basically goes away, even though it's still saying dt. This is an odd equation to me. The average of 2t plus the average of that. Let's keep rocking. See if it becomes clearer as we go. So we have 1 over tau. Now I get this part. G tau minus G naught. So if you have the integral of a derivative of something, then it's just plugging in for that thing, which is this. But I don't understand this terminology here. I guess the line over the top makes it mean the same thing. But like if I have like a integral uh, uh, d dx of x squared dx, then it's just x squared taken from, and you just plug in what you have. So if you, it's like you're taking the derivative of an integral, it's just a thing. You just plug in. So that's what this is right here. It's the integral of a derivative. So we just take the constant and put it in front. And then this is the integral of a derivative. It just goes away, and then you just plug in the thing that you have, which is what I'm doing here, which is 2 squared minus 1 squared. And, if I had a constant in the front, like if it was multiplied by a, it'll just be a times that. And then you'll just have a times each of these, which is what they're doing there. So this is the principle that they're applying. But I just don't see how this means that, but it's just some funny notation, I guess. So that's 3.25. All right. So let me know if you're still with me. Let me know if you have any questions or comments. So this is a bit more complex than my original Virial theorem, but that was the undergraduate method. Going into a bit weird notation, but generally it's familiar. If the motion is periodic, i.e. all coordinates repeat after a certain time, and if tau, which is the interval of time we're talking about, is chosen to be the period, so this one interval of time, everything goes back to where it was before, then the right-hand side of 3.25 vanishes. Uh-oh. That makes sense? Because what this means is we have 1 over tau, g tau minus g tau, because it's starting where it's ending. So that means this equals 0. All right, I'm with them so far. So that means that we have, if I was to just copy down what we have here, let's see where they're going next. This is still in the equation, because again, all of this is still equal to each other. So that means that that equals this. And all they did next was just subtract this from both sides. And thus you get negative on the other side. And then we have that. All right. And then we divide by 2. So we have the average kinetic energy. is negative 1/2 the sum, the average of the sum of the force dot producted with the potential vector dot r I. All right, that makes sense. And this is 3.26. And I'll put if periodic and tau is the period. All right. Equation 3.26 is known as the Virial theorem. And the right-hand side is called the Virial of Clausius. All right, this seems like a good place to stop. We got to the Virial theorem. There's a little bit more, but I said I should finish around 9:30, so I'll go ahead and stop here. So we got to the Virial theorem. Tomorrow what I'll do is, y'all can let me know. Let me know in the comments or in the post on my, maybe I'll make a post now so you all can see it. I'm definitely going to be back because I have an exam on Friday, so I'm going to have to study for this thing. So I'll make a post on my page right now. Go to the STEM channel right now. You'll be able to see it. And I'll ask what to cover on Monday. Continue with Virial theorem details or graduate level problem solving. So let me know now. You can post in the comments. You can reply to the post, and I'll do that tomorrow. But I'll definitely be back. So thank you all for watching. Thank you for commenting, Lisa. Hopefully you enjoyed. Hopefully some of the understanding made it through. So some of the things I can understand, some things I'm still figuring out. And Professor will go over the Virial theorem tomorrow. I'm sure she'll do this derivation. I'll be able to make notes on it. And then we'll probably continue a bit farther from there. And I'll see what input I get from you all. If I don't get any votes or anything, I'll just pick one. I guess I'll see what it'll be. But I'll definitely be back. Thank you, Lisa. Hope to see you again. Good seeing you today. I appreciate the well wishes. And y'all have a good evening.